You know, in every single building with electricity, there's an invisible safety system working around the clock to protect us all. We call it earthing and bonding, and it's basically the fundamental shield against electrical faults. But how does this hidden network actually keep us safe? And more importantly, what happens when it goes wrong?
So, let's get right into it. What really happens when electricity breaks free from its designated circuit? We're going to uncover how this whole system works, and why just a single misconnection can turn a completely safe system into an incredibly dangerous one.
And this right here, this shows you exactly what's at stake. On the left, you've got a safe system. Any stray current has a nice, clear path straight to the ground. No problem. But look at the right. Without that safe path, the entire metal casing of that appliance becomes live. It's literally a lethal trap just waiting for someone to touch it.
So here's the fundamental problem we're trying to solve. During an electrical fault, any piece of metalwork, and I mean anything, from a big switchboard panel to a simple water pipe, can suddenly become energized. If that happens and there's no system in place to manage it, just touching that object could be fatal.
So how do we solve this? Well, the first part of our solution is what I like to call the anchor, protective earthing. Think of it like the ultimate safety drain for electricity. It provides a dedicated, super low resistance path for any fault current to flow away safely into the ground.
And what's absolutely crucial to understand here is that protective earthing is all about human safety. That's its one and only job. It gives that fault current such an easy path back that the surge of electricity becomes massive enough to instantly trip the circuit breaker, shutting off the power long before anyone can get hurt.
Now, you might hear about something called functional earthing, and it's really important not to get the two mixed up. This type of earthing is all about equipment performance. It gives sensitive electronics and IT gear a stable reference point so they work correctly. And yeah, it connects to the same main system, but its primary goal is making sure things run smoothly, not safety.
Okay, so if earthing is our anchor, what's next? Well, we need a safety net, and that's where equipotential bonding comes in. This is where the whole system gets really clever. What bonding does, basically, is it physically links together all the different metal things you could possibly touch at the same time. Think water pipes, radiators, the steel frame of the building, electrical conduits, you name it. The entire point is to make sure that if a fault happens, everything rises to the exact same voltage level. Because if there's no difference in voltage between two things, you simply can't get a shock by touching them both.
But what if just one of those little links, one of those crucial bonding wires is missing? Or maybe it fails over time. This is the moment a totally safe situation can become incredibly dangerous in the blink of an eye.
You see, without that bonding, you can get a massive, and I mean potentially lethal, voltage difference appearing between two separate metal parts. We're talking the full 230 volts of a standard electrical supply. So if you touch a faulty appliance with one hand and a properly grounded water tap with the other, your body suddenly becomes the bridge. The electricity flows right through you. Bonding is what eliminates that voltage difference entirely, preventing this from ever being possible.
Okay, so now we've got our anchor, the earthing, and we've got our safety net, the bonding. Let's put it all together and see how this actually plays out in the real world. We're going to trace the path a fault current takes in the most common types of electrical systems out there. First up, we have the TNS system. Now, the key thing to know about this one is that separate protective earth conductor. Think of it like a dedicated safety wire. When a fault happens, the current has a direct, low-resistance superhighway to get back to the source. This creates a huge surge that trips the breaker almost instantly. It's simple, it's safe, and it's very effective.
Okay, next up is the TNCC system, which is super common. You'll find it in a lot of homes. Here, the neutral and the earth functions are actually combined into a single wire in the supply network. But the end result is pretty much the same. A fault creates a large current that zips back to the source and trips to protection fast.
And finally, we've got the TT system, which you'll often see out in more rural areas. Now, here's the big twist with this one. There's no dedicated return wire from the supplier. The fault current has to travel back to the source through the actual ground. And because soil has a pretty high resistance, the current that flows is usually too small to trip a normal circuit breaker. That is why these systems absolutely must have an RCD, or a residual current device. It's a super sensitive safety switch that can detect even a tiny leak of current and cut the power in milliseconds.
So you see, it doesn't matter what system type you have. The ultimate danger, the real nightmare scenario, is a fault that energizes a piece of metal that isn't bonded. The path for the current is often so weak that it won't trip any protection. That means that piece of metal could stay live at a lethal voltage indefinitely, just waiting. So we've talked about the concept of connecting to the Earth, but how do we actually do it? Let's look at the actual physical parts that create that earthing anchor we were talking about earlier.
Yeah, to get that solid connection to the planet, engineers have a few tools in their toolkit, and which one they use really depends on the ground conditions. They can be these long copper rods that get driven deep into the soil, or copper tapes that are buried in trenches. Sometimes they use big metal plates, or they can even use the steel rebar that's already inside a building's concrete foundation. But you know what? It doesn't matter if it's a rod, a tape, or the building's foundation. The goal is always the same: to create a path with the lowest possible electrical resistance. A low-resistance path is what guarantees that during a fault, the current will be massive enough to operate those protective devices instantly and reliably, every single time.
Okay, so if you take away just 3 things from all of this, let it be these. First, earthing is our anchor. It gives fault current a safe path to follow. Second, bonding is our safety net. It connects all the metal parts together to stop deadly voltage differences. And third, low resistance is the magic ingredient that makes sure the whole system works instantly, right when you need it most.
And really, this quote just says it all, doesn't it? These systems are designed with absolutely no room for error, because a single missed connection can be the difference between a small electrical issue and a real tragedy. It's just a powerful reminder that when it comes to electrical engineering, good design truly does save lives.